欢迎来到第32次复旦核物理前沿开放讲坛。那今天这讲还是由那个
Recording in progress.
王富强教授为我们讲授这个他的系列讲座的第二讲。这个我们的开放讲坛呢是这个主办是由复旦大学核科学技术系现代物理所核物理与离子束应用教育部重点实验室国家自然科学基金委理论物理专款上海核物理理论研究中心主办由这个nuclear science and technology 和核技术刊物协办。那同时呢，将由这个共享平台进行这个转播。那么今天的王富强教授将为我们他的这个 title 是这个 experimental searches for the chiral magnetic effect hint of the signal in global clear at 400 GeV。那富强老师，那你就开始吧。
OK， 好。谢谢国亮的介绍那我就开始了哈就是 so last week I gave a seminar on the same title but with isobar collisions. I will this week continue to tell you more about the experimental searches for the chiral magnetic effect, and I will concentrate on gold-gold collisions, but I will also talk some more about isobar collisions because all are connected. So it's so today's seminar is going to be a bit different from last week's. If you attend last week's seminar, there will be a bit more detailed discussion today. So I hope that I do not lose you. But if you have any questions in the middle, just don't hesitate to ask. Just speak up, and then I will stop. Here is the outline. I will discuss about various methods to eliminate flow-induced backgrounds. So in CME search, in those measurements, the dominant thing is the background, and therefore we spent almost all the effort trying to understand the background, trying to eliminate the background. And then after that, I will continue to discuss some further background contaminations. And those further background contaminations are really from non-flow and the genuine three-particle correlations. And actually, the main part of my talk will be on this point, because the flow-induced background is the major one, but has been studied extensively so far. Now we are at the point to really worry about the next level thing. And then I will discuss the gold-to-gold collision data, and I will try to tell you that there might be some hint of positive CME signal there. And then I will discuss about isobar data. Unfortunately, we do not have a signal there. A signal is consistent with 0, so we can only extract an upper limit. And I will say a few words about that. And finally, summarize and a brief outlook. This is going to be very brief in terms of the physics introduction. So this is really for the benefit of those who could not attend my seminar last week. But I assume that most people are familiar with CME now. So CME is really related to this so-called theta vacuum term of QCD, or of nature of our universe. And this term is topological in the sense that it can have discrete quantum numbers, zero or non-zero quantum numbers. And this is generally referred to as topological charge, or the Chern-Simons winding number. They are all the same thing. It's really due to the gluon field of the vacuum. And because of fluctuations, you can have various vacuum states with different topological charge values. And the normal vacuum we talk about is the zero topological charge, but you can have non-zero topological charge vacuum states. And the good thing about this is that if you have quarks and quarks interact with this gluon field, then the quark chirality can change. And therefore, and that's really the explanation for the UL1 asymmetry, that the axial field, the axial current is not conserved. So the number of left-handed quarks and right-handed quarks are not, total is conserved, but the difference is not conserved. If you have chirality or imbalanced chirality in your system, and if you put your system into a strong magnetic field, then you can see consequence. You can see observable or a charge suppression in your experiment if you do such an experiment. And fortunately, in heavy ion collisions, we do have magnetic field. We think we do have a strong enough magnetic field for a long time, for enough time, at least we hope. And we create this high temperature vacuum, and vacuum can fluctuate, and we can have these topological charge, non-zero topological charge domains, and we really can observe charge suppression if the physics is there and it's really produced. And this is called the chiromagnetic effect. Now, as you can see, that the CME is really addressing a fundamental question in physics. If we observed CME in heavy ion collisions, that could be potentially a very big deal, because it means that we have chirosymmetry restoration, we have deconfinement, we have local parity CP violation in local domains in the strong interaction, and that could offer a solution to the strong CP problem, namely the weak interaction CP violation is not enough to explain the matter-antimatter asymmetry. We really need the strong interaction CP violation, and yet no CP violation has ever been observed in strong interaction. So that's the physics, which is very important. Now, how do we measure charge suppression? Well, we're looking for a charge suppression along the magnetic field, which is on average perpendicular to the impact parameter direction in heavy ion collisions. So we're looking for pions of this configuration. And CG-Evolution proposed an observable azimuthal angular correlation of pairs with respect to the reaction plane. And as you can see, this is called a gamma observable. And for opposite sign, you have charge suppression, so they're back-to-back. This quantity is positive. And for same sign, they should be in the same direction, and therefore it's negative. Now, we expect backgrounds, and naively, the background would be charge independent, or most backgrounds are charge independent. And therefore, we can conveniently remove the background by taking the difference of these two gamma observables. So we concentrate on this delta gamma, which is opposite sign minus same sign. And it should be positive for CME. And we did observe large signal decade ago. And as I told you last week, the measurement, the delta gamma is contaminated by a major background, and the background is really large. And that's the whole problem, because once the background is large, then you really have to be very, very careful about background removal. The background is really due to particle correlations from clusters, from correlations, basically, two particle correlations, like a row decay into two pions. In terms of this variable, the CME pair back-to-back along the y direction will be the same as the variable for a pion pair in the x direction. And this is just because we measure two particles. Once you measure two particles, then the variable is parity even, so-called, and therefore there can be background. And this background is really due to, big part of the background is due to decay, for instance, a row decay like this. And since you have more rows in the reaction plane direction, you have more of those pairs, and those pairs will give you identical gamma as the CME pairs, so you cannot distinguish. And therefore, we have to worry about those background. So if you write it in terms of an expression, the delta gamma would be signal plus background, and this background is given by a number of rows. Just take an example of row decays. Proportional number of rows proportional to the V2, because V2 characterizes the difference between X and Y, and proportional to decay angular correlation, and inversely proportional to the number of pairs. Okay, so therefore it is proportional to V2 over multiplicity on kind of zeros order. So more formally, right, if you expand things, if you worry about other things, now really the delta gamma, it's two particle correlation with respect to the reaction plane. So actually we have three angles, and therefore we actually do three particle correlations, or three-point correlator. You have two angles from the two particles and a third angle from the event plane, from the reaction plane. And we often use three particles. We measure three particle correlation. So the third particle, which is all charged particles, we do not distinguish charges. The third particle gives you the event plane measurement. And the accuracy of that event plane measurement is the V2 of the particle, of the single particle. So we actually do, and if you reconstruct the event plane and do this delta gamma correlation, it's effectively also three particle correlation, because the event plane is determined by all other particles. So it's really an integral of all three particle correlations. And if you look at three particle correlations, you have the signal from CME, and you from and times the V2 of the third particle, and I will get to the details here. And the major background that I have been talking about, due to two particle correlation, right, and due to this two particle cluster V2 and the third particle V2. And since this is three particle correlation, you have a genuine three particle correlation, like from jets, dijets, right? Now the major part is this middle term. This is the two particle background, and then the other two terms are smaller, or the signal is smaller, we know now, and the three particle correlation is also smaller. And just use some shorthand notation. This would be, this I written here the shorthand notation. This would be the main background, and this would be the three particle background, and this would be the signal. And the delta gamma is really the delta C3 divided by V2. Okay, and this V2 is the C particle V2. And now you can see that this main background is really due to the coupling between flow and the non-flow. Right? This is two-particle correlation. It's a genuine two-particle non-flow, and of course three-particle non-flow here. You divide by V2. This V2 is the measured V2. And the measured V2 is not the true V2. It's contaminated by non-flow. And therefore, non-flow comes into here in the V2 measurement. And I should note that, so I use a star asterisk on top of V2 to indicate that this V2 is a measured V2 containing non-flow. And V2 without the asterisk means it's a true V2, a global V2. Does not have to be hydro V2, but it's a global V2. And the background is really due to global V2. Right? It is the correlation between these two particle cluster and a third particle. They're normally uncorrelated, but because of the flow, they are now correlated. So therefore, it's due to the true flow here. So it's actually rather complicated. Now, I should mention here that this V2C perpendicular to the magnetic field is really means that it is the V2 of the C particle with respect to the direction that is perpendicular to the magnetic field, because this is a CME signal which is along the magnetic field. So therefore, if your event plane is not perpendicular to the magnetic field, your CME signal is going to be diluted by a reduction factor, which is given by this V2 divided by V2. Okay, and I will get to that a little bit more later. So this is the delta gamma, we think, signal plus background plus background. The main background is proportional to V2. So the natural thing to think about is to look at delta gamma as a function of V2. Right? That was done a long time ago by Starr. So that's the first event shape engineering measurement. You measure the delta gamma or something similar to delta gamma as a function of the event by event V2 shape. So it's the mean cosine twice angle. And you have a quantity in each event with respect to event plane that you reconstruct elsewhere, right? And as you can see that, first of all, the V2 can be negative. And that's natural because this is really mainly due to statistical fluctuation. And you see a very clean linear dependence in this quantity as a function of this V2 observed. And this tells you that this is really that it's proportional to V2 and it's quite linear. And this is actually determined by mathematics, basically. Now, if you project this to 0 V2, then we think that this is sensitive to CME, right? Sensitive to CME. Now, I'm not going to worry about the three particle part for the moment. Okay, and now we have also new measurements and so forth. And actually, we observed non-zero intercept with good statistics before this statistics. This is from year 4, very old data, and the intercept is consistent with 0. And we actually had new data analyzed by Biao from CCNU many years ago, and we did observe non-zero intercept. Now we know that actually the intercept still contains background, and this is because the V2 that we measure here is really due to statistic fluctuation, or mainly statistic fluctuation. So this V2 is the V2 of your particle of interest with respect to your event plane, right? And if you just look at now the background, which is due to V2 rho, for instance, as a function of V2 pi, the average would be both positive, right? And if you look at event by event, you will see something like this, okay? But once you cut on your final state V2, you're basically selecting slices. Then at 0 V2 pi on final state, you're going to have on average a positive rho V2. As simple as that. and therefore you still have some residual background in the intercept. And it is a lot, it's reduced a lot already, suppressed, but nevertheless, it's non-zero. And the trouble is that we don't know how big that non-zero is. Right? And we did toy model study, and we did see that the intercept is non-zero. So you have a finite V2 rho at 0 final state particle V2. So this is just because we are engineering on statistical fluctuation. Background is suppressed, but not totally eliminated. Now, at LHC, they do not have this problem. And this is because they have a large acceptance detectors, ALICE, both ALICE and CMS. And they can select events according to a Q2 or a V2 quantity at forward detector, at the forward rapidity, using forward detectors. Okay, so that the event selection is done by some phase space that has nothing to do with your particle of interest. And once you do that, now you can look at V2 rho and V2 pi, and this is just a cartoon. We didn't really analyze data. You can do that for rho particles, but this is just an illustration. Now, once you have selected different events, different classes of events, here is the average. Now you select, say, events with larger V2. You are selecting events with this ellipse. You can select events with smaller V2, this ellipse. Okay, but since the selection is not using any particle of interest, they're still perfectly correlated. And therefore, now if you do extrapolation, you're really going to zero. Okay, and this is because the V2 is not dynamical. The fluctuation of V2 is dynamical, not a statistical. And this is ALICE measurement. This is CMS measurement. You do projection to zero. Unfortunately, the intercept is consistent with zero, and therefore only upper limit can be obtained. But this is a promising way to extract possible CME signal. Now, right now, the intercept is all consistent with zero, so we don't worry about further complication. But if we did get a positive intercept, then we have to worry about non-flow effects. And this is because this V2 is measured, contains non-flow. This quantity, which is 3-particle correlator, contains 3-particle correlation, and you have a lot to worry about. But those are good problems to worry, of course, if you have a positive intercept. We're not there yet. Let me talk just one slide on the R variable that some of you may be aware of. So we have this R variable. R variable is really we are looking for charge suppression, right? So this R variable is the mean sign phi relative to the harmonic relative to the event plane of positive particles minus the mean sign of negative particles. And so this is called delta S. And if you have charge suppression, then this delta S would be bigger, right? Because you have now extra pairs, positive go up, negative go down. Therefore, delta S would be bigger because the mean sign is positive and the negative. So positive minus negative would be a bigger number. So if you have CME, this delta S will be bigger than normal. Therefore, the broadening of this delta S distribution is an indication of CME signal. And of course, you do normalization by shuffle events, namely you shuffle positive and negative particles to get rid of charge-dependent correlations. And also you do in-plane and out-of-plane. So out-of-plane is your signal, and in-plane would be your kind of calibration for background. So this is called delta S perb, which is really in-plane, and the delta S would be out-of-plane along the magnetic field direction. And you are measuring the width of this distribution. If it's wider, then it will be consistent with CME. Now, once you are measuring width is nothing but the variance, right? If you do the valence of delta S, you automatically get, sine times sine and cosine times cosine for the perp. And therefore, this is equivalently the delta gamma variable. After many years, we now understand the connection between delta S or the R variable and delta gamma. And actually, once you normalize by shaft width, the 1 / width of this R distribution squared would be equal to multiplicity times delta gamma. And we know that delta gamma is dominated by background, so therefore it is proportional to V2 and inversely proportional to N. So this N times delta gamma would be proportional to V2. So this would be proportional to V2. There were several early claims of CME by R, and many issues were identified. And actually, there was event-shape engineering study in isobar, which is published, and that indicate a V2 independence. Actually, look at event-shape engineering, look at this width, inverse width squared as a function of V2. It's almost independent. If anything, it's a decreasing function, actually. And you would expect this to be increasing, proportional to V2. Okay. And actually, that led to the latest claim by Roy Lacy, that he says that, well, this variable should be scaled by multiplicity, and therefore the isobar R variable is compatible to CME. And now we understand the problem. Actually, this is a new discovery, the latest issue that now we understand. And this is because in the analysis of this R variable so far, it is because you use sub-events, one sub-event to determine event plane and other sub-event to determine delta S. And in the analysis, you swap, so you get 2 delta S for the same event, and you take the average of the two. Now, you are reusing the same event twice, basically. And there is subtle correlation between these two, and we call autocorrelation. And this autocorrelation is giving you all kinds of strange things. We now, and this was actually discovered, pointed out a few years ago already in the preprint, but we did toy model study. Now we really analyze isobar data, but we treat these two separately. We do not average them. We just fill the histogram with twice, with delta each delta S once. Okay, and then you look at the ESE, you see a linear dependence. You do a fit, the intercept is consistent with 0. Of course, your leverage arm is not long, but now we understand this data is very hard to understand, and I was puzzled for actually several years by this data, because we do have goal-to-goal data also shows independence of V2, and that was very strange. Now I'm happy that we really understand it. So really that the R variable is equivalent to delta gamma with a multiplicity. Okay, so the delta gamma there is a multiplicity effect, and that is the isobar multiplicity difference caused this delta gamma ratio to be below 1. In the R variable, this multiplicity is considered, is included implicitly, but the V2 is not included. And remember, in the isobar analysis, we did do delta gamma over V2, but we left out the multiplicity. In the R variable, actually the multiplicity is included already, but the V2 is not included. Okay, so much with that. The main background is due to, say, 2 particle clusters, including resonances. So the natural thing to think about is just look at the invariant mass distribution of delta gamma. And then we did see peaks corresponding to the resonance mass. Okay, so this is a clear demonstration, experimental demonstration that that there is a big piece of background due to resonance decays. We actually did a statistical event shape engineering analysis using invariant mass and try to extract a CME signal. And I'm not going to go into details. We basically look at two different classes according to Q2, and then look at the delta gamma versus delta gamma. And it should be a linear dependence, and the intercept would be the CME with some coefficient. Our statistics are not enough to give us a good measurement, so we can only extract an upper limit of 15% at the 95% confidence level. Okay, so so much about the old or the previous measurements trying to eliminate background. Again, when background is big, is large, you can really rely on models or calculations. You really have to measure it. And the best or most robust measurements would be comparative measurements. Right? You make measurements and compare two measurements, and if you do things properly, if the background cancel, then you're left with signal. And not all, but a lot of major discoveries were achieved that with this method, with comparative measurements. I'm going to talk about two comparative measurements. One is isobar collisions that I've talked about already. I will come back with the non-flow study. The other one is spectator plane versus participant plane. Now, the pros and cons for the spectator versus participant planes, the pro is that both are within the same event. You do two measurements in the same event. So the physics is guaranteed to be identical. The con is that SP, spectator plane, is very hard to measure. We use ZDC using neutrons in the beamline, or single neutrons, and to reconstruct an event plane, a first order event plane. And the resolution is very poor, a lot poorer than the TPC event plane measurement. So that's the con. The pro for isobar collisions is that you can now make both measurements with the TPC. So relatively good event plane resolutions. So you can have more precise measurements. The con is that these two systems are not identical, as I talked about last week. And actually, they are more different than everyone thought a few years ago. So pros and cons. First of all, let me talk about spectator plane and the participant planes. So again, this delta gamma, right? And main background signal. And as you can see, excuse me, sorry. My phone is giving some, okay, good. So here you have the background, and the background is proportional to V2. And the V2 is driven by the participant zone, right? You have high pressure build up in the collision zone, and therefore V2 is determined or is the strongest. The expansion is the strongest along the participant plane of the collision zone. Okay. Now this signal is determined by magnetic field, and this V2 over V2, right? The magnetic field is more aligned with the spectator plane or perpendicular to the spectator plane, because the magnetic field is mainly produced by spectator protons, and therefore the signal would be strongest if you measure the charge suppression with respect to the spectator plane. Right? So therefore now you have two measurements, and actually they depend on background and the signals differently, and there is a nice relationship between the two because the difference is really due to the opening angle between these two planes, right? And this is the factor, the reduction factor, which is the mean cosine twice the difference of the participant plane and the reaction plane, or spectator plane. Therefore, you write the delta gamma signal plus background and signal plus background with respect to SP and the PP. And again, I'm not worrying about the three-particle correlation yet. So with this, it's a simple algebra. You get the fraction of CME to be given by this. Okay, the capital A is the delta gamma measurement with respect to SP over that with respect to PP, and the little a is this angle, which is the ratio of the V2s with respect to SP divided by V2 with respect to PP. So you can make those measurements easily in your data, and you do that event on each event, and you extract a fraction, CME fraction, and this is what we got here, and this is published half a year ago. And this is the FCME in the left plot, and the right plot is the absolute delta gamma CME signal. And CME should be still put in quote. Okay, it's not necessarily the true CME, but we are getting closer to that. First of all, the blue points, peripheral collisions, are consistent with 0, large error bars. The medium central collision, where you expect the CME effect to be the strongest because the magnetic field is the strongest, your event plane determination is the best. You actually see a positive signal. Error bars are relatively large. Significance, in terms of significance, we have about 2 sigma significance, I would say. I should say that those 4 sets of data points are 4 different ways to analyze data with different kinematics, different delta eta gaps for event, sub-event. We use sub-event trying to reduce non-flow contributions. And in terms of the point central value of the points, you do see a decrease in the value. So these 4 points are not independent. So I will say that the data gives you a significance on the order of 2 sigma right now. Now the question is, because in this analysis or in the recipe of this method, we did not worry about the non-flow contamination in V2, and we did not worry about the three-particle, genuine three-particle correlation background. Right? So what are those? Now, this is the C3, delta C3, right? The most important quantity in the FCM here is the A over A, and this is delta gamma over V2, and it's really C3 over V2 square. Okay, so it is C3 SP over V2 SP square divided by C3 PP over V2 PP square. Okay. And as you can see, the SP measurements are fine. We don't have non-flow there because it's an impact prompt direction, so to speak. It's CDC measurement. It's determined by spectator neutrons. There's no non-flow correlation there. So this is a clean measurement, except the error bars are big because the resolution of CDC is poor. This is the TPC measurement, and it contains non-flow. The V2 contains non-flow. The C3 contains 3-particle background in addition to the 2-particle background. Now, the 2-particle background is automatically taken care of in this recipe, not 3-particle background. Okay, and shorthand notations here, and it's really given by this, and this is the epsilon NF is a non-flow fraction in V2 measurement. So by looking at this, if there is no signal, okay, you will still get FCME, and this is a fake FCME. It's a non-flow contamination. For a V2 non-flow, it's in the numerator, and therefore it gives you a positive FCME. So you get a positive fake FCME due to V2 non-flow. And this is actually rather easy to understand because you measure TPC delta gamma or C3, and then you divide by V2 to get delta gamma. If your V2 contains non-flow, your V2 is too big. So therefore your delta gamma is going to be too small or smaller than truth. Okay. And therefore it's more smaller than your ZDC measurement. And the difference between ZDC and TPC is the CME. And now the difference is bigger due to the non-flow contamination in V2. And therefore you get a positive signal, fake signal. Okay. And for 3 particle, actually it's in the denominator, and you're going to get a negative FCME. And this is again because in your TPC measurement, your delta gamma is too big. It's because of the 3 particle contamination. It's bigger than the truth. And therefore you are shrinking the difference between ZDC and TPC. And therefore your signal, your FCME is going to be smaller than the truth. So it's a negative offset. So there is cancellation between the two, partial cancellation. The question is, of course, quantitative, how much is canceled and how much is remaining, right? At the end of the day, your FCME is really given by the right equation. The left equation is just some approximation, and we can do that. And if we measure, this epsilon NF, epsilon 3, then we are there. Okay, the epsilon 2 is measured. It's really just the N delta gamma over V2, because this epsilon 2 is the 2 particle background contamination. Okay, we can estimate the V2 non-flow using AMPT and also data. The 3 particle background contamination, we can only use hygiene because 3 particle correlations are very, very difficult to analyze in data just because of the huge combinatorial background. So we use hygiene to estimate. Epsilon 3 is about 0.02 from hygiene, and epsilon 2 is about 0.2. I can tell you, this is just delta gamma measurement. So it's a factor of 10 smaller for the 3 particle contamination. In hygiene, actually, we did a lot of study of hygiene compared to data, and hygiene is pretty good. And I'm actually more confident in the result than actually half a year ago. All right. With that, right now we have, and this is kind of a private publication in PRC almost a year ago. This is MPT estimate. So this is as a function of central. So this is your fake FCME fraction as a function of centrality. In the right plot is the FCME fake for within 20 to 50% centrality range, but for different ways to analyze data or different ways to obtain the FCME. The red is from AMPT 2 particle correlation estimates, and the blue is from hygiene 3 particle estimates. And one is positive, one is negative. The average or the sum of the 2 is the breakpoints. That should be the net effect. And as you can see, it can be negative because actually the 3 particle contamination from hygiene takes over. It's stronger than your non-flow in V2. Now, of course, the 3 particle is a lot smaller than the 2 particle flow background, which is the main piece, and that main piece is taken care of automatically in this measurement. Put everything on a same plot, you get so the red points excuse me, the solid points, excuse me, the circles are data. So the red circles, red field circles are medium central collision, and the open circles in blue are the peripheral data. And the triangles are the non-flow estimate of FEC FCME. So the blue are for peripheral collisions, and they are consistent with the measurement actually. And actually, as you can see, the background estimate is negative, and the data indicate that they might be negative. So I'm happy with that. And for the medium central collision, except this data point, we can't say much. Actually, the non-flow background estimate is all smaller than data. So I'm hopeful that there may indeed be some hint of positive CME signal in gold data, and those data points from 0 significance is on the order of 2 sigma. From the new background estimate, considering or taking into account further non-flow contamination, because they could be negative, the value could be more positive, but of course you introduce or you bring in additional uncertainty due to the estimate, so the significance does not increase much, so it's still 2 sigma. All right, with that, let me come back to isobar, and hopefully I will be quick here and then I jump to conclusion. So for isobar, so this is gold that we talked about so far. We compare SP with EP or PP. SP does not have any non-flow contamination. It has the flow-induced background, and that's this piece. Right? This is due to coupling between, say, resonance decay and the flow. Okay, it's also there in the ZDC measurement, but no other non-flow contributions. For the TPC measurement, you have additional background, non-flow background. For isobar, it's more complicated because both systems are measured with the TPC. ZDC statistics are not enough, and both are contaminated by non-flow background and 3-particle correlations. So if you do isobar ratio, you get all these terms. Okay, so this red term is this is a non-flow. So this is a non-flow in the V2 measurements in each system, and this is the contribution of the 3-particle correlations. And of course, you take the ratio of the 2 systems, and this part is the main background. It's the flow-induced background. Okay, that people have worried so far, and this is due to 2-particle correlation coupled with V2. Okay, and this is if you factor in the multiplicity, it should be ideally 1. Okay, so really depends on details. So now, what are the details? So these are the details. So this is the formula that I just showed you here, and assuming the difference between the 2 systems is small, which is good, with a good assumption, isobars are still, they are different, but still very close to each other. Then you're talking about non-flow difference between the 2 systems, the 3-particle difference between the 2 systems, and the difference or the ratio of the main flow-induced background. Okay, and this is ideally 1 or naively 1. Okay, so this would be, so this is the money plot from the isobar paper, and the lower dashed line is the new baseline unity if you multiply the multiplicity into delta gamma over V2. Okay, so if everything is scaled with the multiplicity, then actually all the breakpoints are above this dashed line, and that's a signal. And actually, that's what we pointed out in the star paper, of course. But Jim Fen and Su Zhe and Dima, they had a preprint, and they correctly point out that actually, if the background is if the baseline is unity, or on this plot, 90.96%, then all the measurements are above that baseline, on the order of 3 sigma or 2 to 3 sigma. Okay, so they extracted a CME signal of about 9% plus minus 3%, or I'm sorry, 7% plus minus 3%. So 2 to 3 sigma. Okay, and that's what we knew all along with the isobar data. Now, actually, this guy is the main background is not necessarily 1, because this is proportional to the number of two particle clusters, or proportional to low particle. And the multiplicity, the low multiplicity, may not be strictly proportional to pi multiplicity. And you can imagine, actually, if you have a higher density, higher temperature, you would have relatively more rho, larger ratio of rho over pi at high temperature, right? Just from the thermal model, for instance. So therefore, you expect this to be actually larger than 1, because the ruthenium collisions has higher density, because the ruthenium nucleus is smaller. And indeed, this is actually measured by this little r ratio, which is really the difference in the pairs divided by normalized. Okay, and this is also in the isobar paper, and this would be, if just from this pink term, right, this would be the upper pink dashed curve, and therefore the data point, and actually the data points are between these 2 dashed curves. And at this point, without worrying about other non-flow, the answer would be between these 2 dashed lines. And certainly we can do better. And if you now analyze non-flow, and you can actually do this by analyzing data, delta gamma, delta eta, delta phi correlations, to extract non-flow from data. And we did that. Actually, this non-flow in ruthenium is smaller than in zirconium. Why? Because the multiplicity is higher in ruthenium, and therefore there is a larger dilution by multiplicity of the non-flow, because it's inversely proportional to n. And therefore, non-flow in ruthenium is slightly smaller than non-flow in zirconium. So therefore, delta epsilon nf is negative. So this piece is actually positive. Okay, the non-flow V2 contamination. The 3-particle correlation estimate, we use hygiene. And right now the statistics are not good, even though we've run 1 billion hygiene events. Okay. So as you can see that if you try to analyze data, it will be impossible, because the combinatorial background is just too huge. It's n to the cube. Now we do have more hygiene simulation. So we actually shrink this error bar, and this will be in the upcoming publication. But for now, we just use this and plug in the numbers. Everything else is measured. N, V2, epsilon 2, those are all measured. And now the baseline would be the shaded area. Okay, the bandwidth is the uncertainty in the estimate, and we can shrink this uncertainty significantly. So the final publication will be better than this. But taking the first value, now I can do an upper limit, because the data is really consistent with background, and therefore I can extract an upper limit by considering the error bars. Right, the total error bar is 0.7%, which means that the uncertainty, the 1 sigma uncertainty on the CME fraction would be 5%. So therefore, at a 98% confidence level, I can say that the FCME is less than 10% in isobar collisions. Okay. With that, I come to my conclusion. CME is very important. We have large efforts trying to eliminate backgrounds. Now, the main background is the flow-induced background, and that's now understood very well. Okay. Now we are really worrying about the next level of background, the non-flow contamination in V2 measurements and the genuine three-particle correlation background. And I think if we settle down those two pieces, then I think we're done. I can't think of any other background right now. We have various ways to do that. And my best bet is that the spectator plane, participant plane, comparative measurements will be able to get us to a firm conclusion. Again, isobar signal is consistent with 0, and we can set a stringent upper limit in the next publication, and it's going to be the upper limit is going to be less than 10%. Excuse me. We have a hint of finite CME signal from the current goal-to-goal statistics on the order of 2 sigma significance. And right now we did non-flow contamination estimate using models. And actually now we are analyzing data, goal-to-goal data. We did that for isobar already. Now we're just repeating the same analysis on goal-to-goal data. So this will be coming later. And we will have hygiene estimate, but we will have some handle using data to tell us how well hygiene is describing data. So I think we are going to get to a final signal with relatively robust confidence. And we do expect 20, and that's our outlook. We do expect 20 billion events in the next 3 years. And I'm hopeful that we will eventually get to 5 sigma measurement if the current data holds on. That obviously it's a difficult measurement, but all measurements are difficult. All important measurements are difficult. Think about the Higgs discovery, right? From the first round, they had hint of 2 sigma, and they waited, they took more data, and they convinced themselves that there is a Higgs particle. The background is also large. It's a QCD background. So it's a little peak on a big background. So I'm hopeful that we will get to a firm conclusion in a number of years, either a signal or a very stringent upper limit. Right now, the FCME in goal-to-goal collision is on the order of 10%. And it's not contradictory to the isobar data because just from a simple consideration, the signal in these two systems between isobar and goal-to-goal are quite different in terms of the signal to background ratio by a factor of 3. So everything is self-consistent. And I think, yeah, so with that positive note, I conclude and thank you very much. There's still probably a couple of minutes for questions.
好，谢谢付强老师精彩的报告。通过王老师报告，我们了解到这个在 CME 在科学上的重要性，这就是我们也为什么这个费尽千辛万苦在寻找它的原因。但是由于这个存在这个背景上，在实验上其实是非常复杂的。那个王老师为主的这个实验团队尝试了很多不同的方法去研究，也探索了这个 CME 存在的可能性。目前呢，还有很多工作正在开展，我们也期待未来有更好的理解。那么下面呢，我们有一段时间可以向王老师提问啊。那么大家有什么问题吗？王老师，王群老师，你有问题吗？
富强啊，挺好的。我这个报告，对我想问一下，你这个所谓的估计是10%，你是什么的东西的10%啊？
是我们 measure inclusive delta gamma 对吧？就是那个 delta gamma variable
啊 ，delta gamma 的 10%，
10%有可能是就是 upper limit， 像 isobar upper limit 10% of that delta gamma is
delta gamma，
yeah delta gamma yes
那就是和那个谁迪马卡泽耶夫和那个廖金峰他们估计的是差不多的，他是6%是吧？
他们是7% plus 7 plus minus 3 they have a yeah but that's yeah we are way
这
beyond
是理论，这是理论。
well yeah it's
那就是和你这个upper limit， 你只是给那个 upper limit， 因为你理论你那个实验那个误差太大了，你只能给一个 upper limit， 对吧
right 但是他们理论那个是他们的 baseline 就是用 1是吧？他们没有
那你觉得是不对的是吧？还是
那个是不对，那个是 naive 的 baseline。我们现在就是我们现在知道的就比那个要好，
要好
more understanding。对，
Okay,
如果是 background 如果是 baseline 是1的话，那么我们早就 conclude 这个是 3 sigma measurement。
OK
yeah。
那就是说也就是说，如果你这个在2023年、2025年这个 run 这个有这个20 billion go 的 events， 那你看你比你这个2.4个 billion 要多了10倍了，对不对？将近10倍了。那你这个误差，你期望就是说你期待能减小到，比如说
statistical 误差减少3倍，对吧？
减小3倍 ，OK。
所以到那时候是 dominated by systematic uncertainty 所以但是我觉得 with more data， 我们的 systematic uncertainty 会更 shrink。systematic uncertainty 是一个比较 conservative 的estimate。在那个 Gold 那个 PRL publication 里面，我们的 systematic uncertainty estimate 其实是要比 isobar 的 systematic uncertainty estimate 有 conservative 的多 factor of 2。所以呢systematic uncertainty 是一个，就是说如果25年有那么多 data 的话，我觉得就 determined by systematic uncertainty。那么当然也 depends on 你的 signal 有多大，对吧？如果你的 signal
对，你 signal 太小，你仍然不行，
也不行的，对，也不行的。如果你 signal 确实如果是 5% or above 5%， 那我觉得5 sigma 是有希望的，
有希望 ，OK。
对，
好。
如果 nature is kind，right？
那当然，如果因为这个东西你也不知道是多少嘛，是吧
？Right， 现在只是 2 sigma，right？
对，
就是 fluctuations。
是的。OK，Thank you。
好的，大家还有问题吗？金辉，
富强，
金辉你好。
富强，非常精彩的报告。你能回到第15页吗
？OK。
对，我想问一下第15页那个德莱伊塔，你的德莱伊塔从0.1到0.3，我想再看一下那个就是那个 gap， 你放从0.1到0.3，差别的，对我没太理解为什么那么大。
OK， 那个
slide 15，对。
三号一次 slow。OK，
对，这里，
对，
就从还可以，就是德莱伊塔从0.1到0.3，其实应该变化不大，但我刚才对，那我没什么问题。对，富强，我再问一下，那就其实到23、25年的时候，其实对，到时候我们会有那个，比如说我们有 ITPC 的话，你的 tracking efficiency 会提高，比如杨慈他们做过的，就是会提高，比较明显，所以到时我们应该会收到更多的 charge particle， 对不对
？Yes, a lot. So a lot more than factor of 10. Yes, yeah.
OK， 没有 OK， 我就问这个问题，我刚才这个0.1、0.3，我刚才没看特别清楚。OK， 好 ，Thank you。
富强老师，我想请教一个问题，那个就是你提到这个3 particle 主要是来自于 jet 的那个 contribution， 它对 XRD 是一个负的贡献。 那么是不是这个怎么理解？是不是可以在那个就是 peripheral collision 的时候，我们甚至可以看到负的 FCME， 或者在 high PT 的时候可以看到？
statistical comparison，但是对，如果如果是在 peripheral collision 用 ZDC、TPC 来 measure 的话，也可能会看到负的 FCME。
OK， 现在STAR 的话，好像也看到这个负的，就是这张图上也有负的，是吧
？Right， 像比如说你这个 peripheral collision 是吧？这两个点。
对吧？是的，对。
可以说 consistent with zero， 但是也可能是负的。
是的。另外一个问题是，您能到13页吗
？13页 ，OK。
对的。就是这个工作里面，这个 CME， 就是你中间这个卡通这个图，这个 CME V2 feature 这个图，的下面这个相对于 participant 里面这个 CME 乘上 A。也就是说 ，CME 这个相对于这个 reaction plan 和这个 participant plan， 它差是 A 倍，但是这个 A 倍呢，刚好是你定义的下面这个 V2 的 ratio， 就是说也有可能不是这个和这个 CME 的信号和 V2 可能是两种不同的东西，所以有可能不是和这个 A 刚好有这个 A 倍的关系。
对，这个就是如果是只是这两个 plan 的话，对吧 ？participant plan 跟 spectator plan， 那么这个就是同一个 A， 因为这个 A 其实就是这两个 plan 之间的这个角度决定的，就相当于是说你做 projection from SP onto PP 是这个角度，你做 projection from PP to SP 也是同一个角度。你刚才说的是，如果 magnetic field 它跟 spectator plan 又不一样，那么这个 magnetic field 这个 CME 那个 reduction 真正 CME 的 reduction 不是 A 了，而是另外一个，所以呢，我们这个 measurement 这个 measure 出来的东西是什么东西呢？就是如果说我们得到这个 FCME， 这个 FCME 是什么东西呢？这个 FCME 其实是真正的 CME project onto spectator plan， 这样一个平均值。所以呢 ，has measurement， 就只是说 interpretation。如果说这个 magnetic field 跟 spectator plan 还是有区别的，我想肯定是有些区别的因为 magnetic field 有 participants 的 contribution，for example， 对吧？那么这个就是相当于是一个interpretation 的问题了。也就是 measurement 就 measure 的东西是什么 ？measure 的东西就是你的 CME signal measured with respect to the spectator plan。
好的，因为我们最近也在做这个类似的这个研究，就是我们发现这个 CME 的 signal 在那个 MT 模型里面，我引入以后发现，就是说它其实它是在不同阶段的时候，这个 ratio 是在变的，就是和这个 A 的话，可能就会有一些区别。这个我们最近在写一篇 paper，
OK，
到时候请你给我们指点。
OK， 我同意，肯定是会有变化的，肯定是就是说这样测量出来的话，可能并不是理论上的 CME 但是是一个 projection。
好的，我理解你的这个观点OK， 凯佳对不对？你好，
我有一个问题，就是您里面最后那个 conclusion 说那个 gold 里面它可能有10%， 但是 upper limit。那相比于 gold 的话，如果是在就是 lead 它这个 signal 会就 L2C 的那样的话，它这个 signal 是会增大呢，还是或者说会减小呢？
就是说compare RIC 跟 LHC 大小是一样的，差不多的。那么这个很难说，就是说理论上我觉得是说理论的这个consensus 是说在 LHC 这么大的能量下面它的 CME signal 可能会比 RIC 要小因为它那个可能一个 argument 是说 magnetic field 的 duration 太短了但是原则上来说谁也都不知道，就是到底是 LHC 大还是 RIC 更大那么有关 background 也很难说 background 是什么呢 background 是我们说是 inversely proportional to multiplicity 那么这样来说的话background 肯定是 LHC 要更小一些，因为它 multiplicity 更大但是呢它的 LHC 的那个可能温度更高的话，它的 cluster two particle cluster 就更多那么它的相当于 number of rows 会更多虽然说它的multiplicity dilution 更大，所以呢这个 effect 恐怕就 cancel 掉了也就是说有关 background 可能是 LHC 跟 RIC 可能差不多。
喂，
所以就是不是很确定到底是 RIC 还是 LHC， 它 signal 更 strong。
Right, signal to background ratio 没法确定，对，这理论上都没法确定，对吧？实验上的话 LHC 现在还没法用这个SPPP 来做 measurement， 因为他们的 ZDC 的这个 capability 不太够，没有 segmentation， 它就是说他们的segmentation 太小了。就没法定这个 angle， 他们只能定这个能量。
好的，谢谢。
喂，那个对等一下，说到刚刚这个问题，我先插一句，我先打个广告，就是说，富强，你可以，我现在打字打到那个对话框里，这是我们昨天刚放到 archive 上的一篇文章，是在 LHC 能区，我们就用一个很简单的 blast wave 加 LCC， 我们可以同时描述 CME 和 CMW 这两个观测量在这个就是爱丽丝的测量结果。然后这个你有兴趣看一眼，回头这个对我们可以再做更多的讨论。就是定量的，对定量的，我们把 CME 跟 CMW 两个 observable 两个 measurement 联系到一起了，发现它可以同时就这个呢跟刚你讨论的这个是跟刚你提这观点是一致的，就是说在 LHC 能区，它这个就是这些 background 的理解，就相比 RIC 它其实还是简单很多 ，multiplicity 更高，然后那些 non-flow 呢。相比 RIC 都要小一些，所以在这块就是我们觉得用一个背景就已经可以很好的解释了。那么当然在这个 RIC 这个第一点的这块情况还是比较复杂的。行，我就插入这么多，不好意思。下面还是请伊利吧。
好，请那个山大的伊利老师提问。
就是在现在这个图上就是有这个不同的 plan 的方向，来确定这个 B field 的方向，我就想问。就说如果用这个 polarized 的 photon-nucleon 或者 photon-photon interaction 给出的dilepton 或者 dipion 它们这个 phi modulation 有没有可能够更直接的来确定这个 B field 的方向？
有可能，我没仔细想过肯定是有可能的，但是在这个主要是 peripheral collision 对吧 ？ultra peripheral collisions。如果 medium central collision 如果这么确定的话，那就完全有可能了，因为这个 CME signal 它是在 medium central collision， 在 peripheral collision 恐怕就没有。但是如果能够用peripheral collision 这个photon-nucleus interaction 来确定这个方向的话，那应该是可以的。我是不是 lost 掉了？
没有，可以。
OK，
你说 好像没有其他问题。赵杰有问题吗？赵杰有个问题。
我有个问题吧，就是跟着刚才伊利讲的呢，就是说他是讲这个 photon nuclear 是不是可以在这个 AA 里测这个磁场？就是我是在想，就是上次王群老师不是问你吗？就是这个有没有一个跟就是磁场有关的背景，就是 isobar 这样或者是什么玩意儿？就是我是在想这个就是还是 photon nuclear interaction 产生的这个肉，是吧？它也是个背景，但是这个 photon nuclear interaction 产生这个肉跟这个 Z 是有关的，就是其实就是跟磁场有关，对吧？就相当于它就是跟 Z 的频繁有关嘛。
OK，
也就是说，就是 isobars 这两个，如果是有一些 photon nuclear interaction 产生的这个肉，它也有一些difference，而且是跟磁场有关的一个 difference。
OK，
大概就是这个意思吧。
也就是说，这个 flow background 跟你的 signal 可能是 coupled。
对啊，而且这种肉呢 ，decay 就是跟刚才那个伊利说的有那么一回事儿。这个 decay 的肉它是跟磁场的方向有关的，而且它的大小跟磁场的 b square 有关，而且它的方向跟 b 更接近。
OK。
所以如果 isobars 的话，你这个就其实上就是跟 signal 一样的。
OK，yeah， I don't disagree，yeah， 这就是说，可能需要具体的 study 了。
对，我大概估计了一下，但是这个我已经估计了一下了，比较小，1/1000吧，就是它可能给 isobars 可能造成1/1000的 difference， 大概这个量级左右吧，可能大个5倍10倍也不一定，我不知道。
OK， 那你说这个在 medium central collision 20 to 50%？
这也可以啊，当然可以啊。这个在 medium central collision 当然也有这个 photon nuclear interaction， 这个我们 STAR 不是张方面不是测过这个吗？就是测过这个吉普赛的这个 low PT 的这个吉普赛的 coherent 的
OK， 那这个需要一个 model study 了，对吧？
对，我是粗略的估计了一下 model study 当然也可以。
对，但是估计就关键是估计把写下来嘛，就更容易懂一些。但是，
对，可以再仔细看一看。我大概就是说跟你们说，就是这样提到这个问题嘛，所以就插一句。
OK。
好的，那个时间不知不觉过得很快。我们非常感谢富强老师这两次论坛给我们系统介绍了这个 CME， 尤其是在实验上去寻找这个 CME 的这个最新的这些进展。那么我们国内也有很多做 CME 的这个师，然后也希望以后呢跟富强老师呢能够加强交流我们一起去在这个方向上做一些事情。谢谢富强老师。
OK，
谢谢大家。拜拜。
拜。